The Greater Miami Flood Defense Network operated as a distributed control system spanning 47 kilometers of coastline, comprising 156 hydraulic sector gates, 2,847 environmental sensors, and 34 autonomous pumping stations linked through a fiber optic backbone to a central SCADA node housed in a reinforced facility near Miami International Airport. Each sector gate measured between 8 and 22 meters in width and utilized a dual-piston hydraulic system capable of generating 340 bar of closure pressure, designed to resist Category 5 hurricane storm surge while maintaining millimeter-precise positioning based on real-time tidal data. The network architecture followed a hierarchical control model. Sensor arrays transmitted water level, salinity, and meteorological data via encrypted channels to regional substations, which aggregated this information and forwarded it to the master controller using TLS 1.3 encryption with X.509 certificate-based authentication. The system's operational philosophy adhered to the fail-closed paradigm, a design decision rooted in the catastrophic flooding events of 2017 and 2023, which mandated that any loss of verified communication between the central node and field devices would trigger an immediate transition to maximum defensive posture, all gates sealed, all pumps disabled, all manual overrides subject to cryptographic validation. This architecture had operated without significant incident for 9 years, processing approximately 18 million sensor readings daily and executing over 400 gate position adjustments per tidal cycle, maintaining the delicate equilibrium between a city built at an average elevation of 1.8 meters above sea level and an ocean that rose measurably each year. The certification infrastructure supporting this system relied on a network of digital certificates issued by a private certificate authority operated by the Army Corps of Engineers, with root certificates embedded in the firmware of every controller, substation, and sensor node, creating a web of cryptographic trust that validated every data packet, every command, every acknowledgement flowing through the system. On the morning of September 12th at 06:47:33 UTC, the primary SSL/TLS certificate authorizing communication between the central SCADA node and the coastal sensor network reached its programmed expiration timestamp, a date that had been set during the system's initial deployment but had become buried in 3,200 pages of technical documentation across 17 different engineering firms and government agencies. The certificate expiration did not announce itself with alarms or warnings. It manifested as a sudden inability of the central SCADA node to validate incoming sensor data, which the system's security protocols interpreted not as an administrative oversight, but as a potential man-in-the-middle attack or network compromise. At 06:47:34 UTC, the master controller's authentication module rejected 2,847 sensor packets simultaneously, logging each as untrusted source in its security event database, and in accordance with its threat response programming, initiated a Level 5 security lockdown that cascaded through the network in 1.3 seconds. Regional substations, receiving no validated commands from the central node and unable to re-establish certified connections, executed their own fail-closed protocols, sending shutdown commands to every hydraulic actuator, every motor controller, every variable frequency drive in their respective sectors. The 156 sector gates, which at that moment were positioned in their normal tidal configuration, partially open to allow the outflow of the previous night's stormwater accumulation, received emergency closure commands authenticated by the still valid substation certificates, and their hydraulic pistons began extending at maximum rated speed, consuming 680 liters of hydraulic fluid per gate and generating vibrations measurable on seismographs at Florida International University's Geology Department. Within 4 minutes of the certificate expiration, every gate along Miami's waterfront had achieved full mechanical closure, their polyurethane seals compressed against reinforced concrete frames with a force of 89 metric tons per linear meter, creating a watertight barrier that extended from 2.4 meters below sea level to 4.8 meters above it. The pumping stations, governed by the same security architecture, entered a protective shutdown mode that drained their prime, closed their intake valves, and disabled their 15-megawatt motors, eliminating the system's capacity to move 340 cubic meters of water per second from the city's stormwater collection network into the ocean. Human operators at the Flood Control District's Operations Center watched this cascade unfold across their monitoring screens, initially interpreting it as a drill or a sensor malfunction, then attempting to issue manual override commands through the system's authenticated control interface, only to have each command rejected with the cryptic error message, "Certificate validation failed, security override denied, manual intervention requires valid trust chain." The system, designed to resist tampering even from authorized personnel during a potential cyber attack, had effectively locked out its own administrators, trapping the city inside a barrier designed to protect it. At 07:15 UTC, while engineers at the Operations Center were still attempting to diagnose the certificate failure, the National Weather Service's automated warning system issued a bulletin for a rapidly intensifying tropical moisture surge approaching Miami-Dade County from the southwest, a meteorological phenomenon characterized by the convergence of a low-pressure trough over the Florida Straits and a moisture-rich air mass from the Caribbean, producing localized rainfall rates exceeding 120 millimeters per hour. The storm system, designated as Tropical Depression TD-18, lacked the rotational organization to qualify as a named hurricane, but carried an atmospheric water content comparable to Category 2 systems, and its predicted track placed the center of maximum precipitation directly over the urbanized corridor between downtown Miami and Miami Beach. Miami's stormwater infrastructure had been engineered to handle rainfall events up to the 50-year recurrence interval, approximately 200 millimeters in 24 hours, by collecting surface runoff through 1,847 kilometers of underground drainage pipes, channeling it into retention basins and coastal pump stations, and discharging it into Biscayne Bay during low tide windows, when the differential head allowed gravity drainage, or when the automated pumps could overcome the tidal back pressure. This system, however, operated under the assumption that the sector gates would remain in their algorithmically optimized positions and that the pump stations would respond to water level sensors distributed throughout the drainage network. With the gates sealed and the pumps offline, the city's stormwater system had been transformed from a dynamic hydraulic network into a closed basin with no outlet, its capacity limited to the volume of the pipe network itself, approximately 2.8 million cubic meters, and the storage capacity of its retention basins, which, at current fill levels, could absorb an additional 1.1 million cubic meters before reaching overflow conditions. At 0842 UTC, the leading edge of TD-18 crossed the coastline near Homestead, and rain began falling across Miami-Dade County at rates that quickly exceeded 90 millimeters per hour, producing runoff that flowed into storm drains designed to carry it, but which now simply filled like tanks, the water rising through the pipe network toward the street-level grates that served as its only expansion volume. The physics of the trapped water followed principles that would have been familiar to any hydraulic engineer. The closed sector gates created a boundary condition that prevented mass transfer between the urban basin and the ocean, while the continued input from rainfall created a positive accumulation rate that could only be resolved through rising water levels until equilibrium was achieved through evaporation, infiltration, or structural failure. Miami's urban surface area measured approximately 143 square kilometers, of which roughly 68% was impervious surface, concrete, asphalt, buildings that converted rainfall directly to runoff with minimal absorption. At the observed precipitation rate of 95 millimeters per hour, this translated to an inflow rate of approximately 2,540 cubic meters per minute entering the stormwater system, a volume that under normal conditions would have been distributed between retention storage and continuous pumping to the bay. The retention basins reached their maximum capacity at 11:23 UTC, just 2 hours and 41 minutes after rainfall began, as verified by telemetry from the 73 basin-level sensors that continued to function despite the network lockout, their data streams visible to operators who could observe but not control the system. Once the basins filled, the incoming stormwater had nowhere to go but up, reversing its flow through the drainage network and emerging from street-level drains, catch basins, and low-lying drainage outfalls throughout the city. The flooding pattern was not uniform. It concentrated first in the naturally low areas, the historic Overtown district, portions of Liberty City, the western edges of Miami Beach, where elevations ranged from 0.3 to 1.1 meters above mean sea level, and where the streets began to flood when the subsurface pipe network pressurized sufficiently to overcome the vertical head. Residents in these areas initially perceived the flooding as typical heavy rain accumulation, a familiar if unwelcome occurrence during tropical weather events, but the water's behavior was anomalous. It rose steadily rather than draining away. It emerged from drainage grates with increasing force as the subsurface pressure built, and it showed no response to the cessation of rainfall during brief periods when the storm bands shifted. By 1300 UTC, water depths in the lowest elevation areas exceeded 0.6 meters, and the flooding front was advancing into previously dry areas at a rate correlated directly with the topographic gradient, creating an expanding pool that respected Miami's elevation contours as precisely as a reservoir filling behind a dam. At the Flood Control District's Emergency Operations Center, a team of 17 engineers and system administrators had escalated the crisis through 3 levels of organizational hierarchy and were now engaged in a desperate attempt to regain control of the physical infrastructure through means the system's designers had explicitly tried to prevent, bypassing the digital control layer entirely. Each sector gate installation included a manual override mechanism, a hydraulic hand pump and mechanical valve system that could theoretically open the gates independent of electronic control. But accessing the system required both physical presence at the gate location and authorization via a cryptographic key stored on hardware security modules distributed to senior engineering staff. The security architecture had been designed to prevent a scenario where compromised credentials or a rogue operator could open the flood defenses during a hurricane, potentially flooding the city deliberately. And it accomplished this by requiring that manual override commands be validated against the same certificate chain that had just expired. Engineer Marcus Chen, the Flood Control District's Deputy Director of Infrastructure Security, reached Gate Sector 23 on Brickell Avenue at 1447 UTC, accompanied by 2 technicians carrying the manual override kit, a reinforced case containing the hydraulic hand pump, high-pressure hoses, and the hardware security module that stored his cryptographic credentials. The gate itself was a massive concrete and steel structure embedded in a reinforced channel, its hydraulic cylinders visible through inspection ports, their chrome piston rods extended to maximum closure position. Chen connected the manual pump to the auxiliary hydraulic port, a procedure he had performed successfully during training exercises, and inserted his security module into the gate's local control panel, expecting the system to validate his credentials and allow him to retract the pistons manually. The panel's display, illuminated with a certificate validation screen, attempted to verify Chen's credentials against the expired network certificate, failed and displayed the message, "Security validation error, manual override denied, system in lockdown mode, contact central authority." The paradox was complete. The central authority that the system demanded he contact was the same system that had locked itself out, and the security mechanism designed to protect against unauthorized access had become absolute, recognizing no exception for emergency conditions or administrative override, because such exceptions would have created the very vulnerabilities the system was designed to eliminate. Chan and his team repeated this procedure at 4 additional gate sites with identical results, while behind them, water that had accumulated to depths exceeding 1 meter lapped at the concrete foundations of the gates that could have released it, separated from the ocean, where the tide was currently 0.4 meters below normal high water, by a barrier that was both completely functional and completely inaccessible. By 16 UTC, the hydraulic situation inside Miami's flood defense perimeter had evolved into a scenario that inverted the system's design assumptions. Instead of protecting against high external water levels threatening a low internal area, the gates were now retaining high internal water levels against a relatively low external condition. Tidal gauges on the ocean side of the barrier recorded water levels of 0.73 meters above mean sea level, reflecting a normal tidal state modified slightly by the storm's atmospheric pressure effects, while water level sensors on the interior side, those that were above water and still transmitting data, recorded levels ranging from 1.2 to 2.4 meters above mean sea level, depending on local topography, creating a pressure differential of 0.5 to 1.7 meters of head acting from the inside of the barrier outward. This represented a loading condition the gates had never been designed to resist. Their structural calculations and hydraulic system specifications assumed external pressure from storm surge, with internal water at or near ground level. But the current condition reversed this, placing tensile rather than compressive loads on the gate seals and creating outward-directed hydraulic forces on the piston rods that opposed their normal operational loading. Structural engineers, hastily convened by the Army Corps of Engineers, ran finite element analyses of the gate structures under the inverted loading condition and determined that the gates would maintain structural integrity up to an internal water level of approximately 3.8 meters above mean sea level, beyond which the probability of seal failure or hydraulic system damage increased exponentially, and that any such failure would likely be catastrophic, potentially blowing a gate open suddenly and releasing a large volume of water into the bay in an uncontrolled manner that could damage nearby structures and vessels. The rainfall, meanwhile, had settled into a persistent pattern, with TD-18 stalling over Miami-Dade County in a configuration meteorologists would later classify as a training echo event, where successive rain bands followed nearly identical tracks, maintaining an average precipitation rate of 65 millimeters per hour across the urban core. The accumulated rainfall total at Miami International Airport reached 384 millimeters at 18 UTC, and simple volumetric calculation indicated that approximately 37 million cubic meters of water had fallen on the impervious surfaces within the flood defense perimeter, of which the stormwater system had absorbed roughly 4 million cubic meters in its pipe network and retention basins, leaving 33 million cubic meters that had nowhere to go but onto the streets, into buildings, and into the slowly rising pool that was transforming Miami's street grid into a network of canals. At 19:30 UTC, nearly 13 hours into the crisis, a team of network security specialists from the Department of Homeland Security's Cybersecurity and Infrastructure Security Agency had established a command post at the SCADA facility and were attempting to resolve the certificate failure through methods that ranged from standard IT procedures to experimental interventions that violated multiple security protocols but were deemed necessary given the escalating emergency. The expired certificate existed as a digital file in the SCADA server's certificate store, and the straightforward solution would be to generate a new certificate from the private certificate authority, install it on the server, and restart the authentication services, a procedure that would normally require approximately 15 minutes. However, the private certificate authority itself was offline, a security measure implemented after a 2024 incident where an online certificate authority had been compromised. The CA existed as an air-gapped system in a secure facility in Arlington, Virginia, accessible only through scheduled maintenance windows and requiring physical presence of at least 2 authorized administrators with separate authentication credentials. The personnel with the necessary credentials and access were identified. One was in Singapore attending a conference, the other was unreachable somewhere in the Appalachian Trail. And even if they could be located and transported to Arlington immediately, the process of generating, validating, and distributing new certificates through the proper chain of custody would require a minimum of 8 hours under the most optimistic scenario. CISA's senior cryptographer, Dr. Sarah Okonkwo, proposed an alternative. Generate a temporary self-signed certificate on the SCADA server itself, manually install matching certificates on each of the 34 regional substations, and force the system to accept the new trust chain, essentially performing a field surgery on the security infrastructure that would restore functionality while bypassing the compromised certificate authority. This approach faced 3 technical obstacles. First, the SCADA server's security configuration prevented local certificate generation without validation from the CA. Second, the regional substations were distributed across 47 kilometers of now flooded infrastructure, many in locations currently inaccessible due to water depths exceeding safe waiting limits. And third, the system's firmware included tamper detection mechanisms that would interpret unauthorized certificate modifications as evidence of compromise and could potentially trigger an even more severe lockdown state that would render the entire system unrecoverable without complete firmware reflashing of every device. Nevertheless, at 2015 UTC, Dr. Okonkwo initiated the certificate generation process, using administrative access to override the server's security policies, and successfully created a new root certificate and corresponding device certificates, the digital files that represented the only path to regaining control of the physical infrastructure that held Miami hostage. The new certificates existed as encrypted files on a secure USB drive in Dr. Okonkwo's possession, but transferring these digital artifacts to the 34 regional substations distributed throughout a flooding city presented a logistics challenge that merged cybersecurity requirements with disaster response constraints. Each substation required physical access. The substation's network interfaces had been deliberately isolated from remote administration to prevent cyber attacks, and the certificate installation procedure required connecting a laptop to the substation's maintenance port, authenticating with local credentials, uploading the certificate file, and manually restarting the substation's control services, a process estimated at 12 minutes per site under optimal conditions. The Flood Control District mobilized every available engineer, technician, and administrator with the necessary access credentials and security training, assembling teams of 2 people per vehicle to maximize coverage while maintaining the security protocol that required 2-person authentication for any modification to critical infrastructure. The teams departed the operations center at 21:43 UTC in a convoy of 12 high-clearance trucks and 2 airboats requisitioned from the Everglades National Park Service, equipped with waterproof cases containing laptops, satellite phones, and copies of the certificate files, each encrypted with a unique key that would be transmitted to the teams via secure channel only when they reached their assigned substations. The flooding conditions they drove into had evolved from street-level water accumulation into a genuine urban inundation event, with water depths exceeding 1.5 meters in the low-lying districts and approaching 0.8 meters even in elevated areas like Brickell and portions of Coral Gables, and the water continued to rise at an average rate of 4.7 centimeters per hour as TD-18 continued its relentless precipitation. Team 7, assigned to substations in the Design District and Wynwood, reported at 22:31 UTC that their truck had stalled in water exceeding its fording depth on North Miami Avenue, forcing them to abandon the vehicle and proceed on foot through chest-deep water, carrying their equipment in waterproof bags, navigating by GPS and the dim glow of emergency lighting from buildings whose first floors were now submerged. Team 3, attempting to reach the Miami Beach substations, discovered that the Julia Tuttle Causeway was impassable, with water overtopping the roadway and creating a current strong enough to move vehicles, forcing them to requisition one of the airboats and cross Biscayne Bay through conditions that the boat's pilot, a National Park Service ranger named Carlos Mendez, later described as moderate sea state in the middle of a city. By midnight UTC, 6 of the 12 teams had successfully reached their assigned substations, completed the certificate installation procedure, and reported that their substations had successfully re-established authenticated communication with the central SCADA node. But 28 substations remained offline, and the master controller's programming required validation from at least 85% of the regional nodes, 29 substations, before it would exit lockdown mode and restore operational control. At 02:17 UTC, 20 hours into the emergency, Team 11 successfully completed the certificate installation at Substation 29, the threshold required to achieve the 85% quorum, and transmitted the completion code to the Operations Center, where controllers watched the master SCADA system's status display transition from red to amber as it began the validation process, querying each restored substation, verifying certificate authenticity, and rebuilding its trust map of the network. The validation sequence completed at 02:22 UTC, and the system status transitioned to green with the message "Network Integrity Restored, Lockdown Lifted, Manual Control Enabled." And for the first time in 19 hours and 35 minutes, human operators could issue commands to the flood defense infrastructure. The immediate priority was opening the sector gates to allow the accumulated water to drain, but this operation required careful sequencing to prevent structural damage from uncontrolled outflow and to account for the current tidal state, It was approaching high tide, with external water levels that would soon exceed some of the internal levels in the higher elevation areas, potentially creating backflow conditions if gates were opened prematurely. The chief hydraulic engineer, Michael Torres, executed the drainage plan his team had developed during the long hours of lockout, beginning with the gates in the lowest elevation sectors where the internal water levels were highest and the pressure differential most favorable, opening each gate incrementally to control the outflow rate, monitoring the structural loads on the gate mechanisms, and proceeding to successive sectors as internal water levels decreased. Gate Sector 12 in Overtown received the first opening command at 0231 UTC, and its hydraulic pistons began retracting at the reduced rate Torres had specified, slowly creating a gap between the gate and its frame through which water began to flow, initially as a trickle that grew to a substantial current as the gate opening increased, the water accelerating through the constriction and entering Biscayne Bay in a turbulent plume visible in the floodlights mounted on the gate structure. The flow rate through the fully opened gate reached approximately 47 cubic meters per second, and the water level in the immediate vicinity began to drop measurably, falling 8 centimeters in the first 15 minutes, but with internal water volumes estimated at 33 million cubic meters and total drainage capacity even with all gates open calculated at approximately 1,200 cubic meters per second, the mathematics indicated that complete drainage would require a minimum of 7 hours under the most optimistic conditions, assuming no additional rainfall and favorable tidal conditions. The rainfall from TD18 finally diminished at 0450 UTC, the storm system having stalled over Miami for 21 hours and deposited a total of 547 millimeters of precipitation, a rainfall total that exceeded the 100-year recurrence interval and that would have challenged Miami's stormwater infrastructure even under normal operational conditions. By 08 UTC, with all 156 sector gates open and the tidal cycle approaching low water, creating maximum differential head for drainage, the floodwaters had receded from the higher elevation areas, but water depths in the lowest lying districts still exceeded 0.4 meters, and the pumping stations, now reactivated, were running at full capacity to evacuate water from retention basins and the pressurized drainage network. The human cost of the event included 3 confirmed fatalities, 2 elderly residents who had been unable to evacuate from ground-floor apartments, and 1 emergency responder whose vehicle had been swept off a submerged roadway, and 1,247 individuals requiring emergency medical attention for injuries ranging from waterborne illness to electrical shock from contact with submerged electrical systems. The economic impact, calculated over the subsequent weeks by a joint assessment team from FEMA and the Army Corps of Engineers, totaled approximately $8.7 billion in direct damages, including 34,000 vehicles destroyed by water intrusion, 12,400 residential structures with major flood damage, 890 commercial buildings requiring structural remediation, and the complete loss of electrical and data infrastructure in the urban core that required 14 days to restore to minimal functionality. The technical investigation, led by the National Institute of Standards and Technology, identified the root cause as a configuration management failure. The certificate expiration date had been set during the system's initial deployment in 2016 using a standard 10-year validity period, but the expiration date had not been entered into any of the automated monitoring systems, maintenance schedules, or renewal procedures that governed the network's ongoing operation, a single metadata entry overlooked among 3.2 million configuration parameters distributed across 2,881 devices. The investigation's final report, published 7 months later, included 47 specific recommendations, but its executive summary concluded with a single observation that captured the essential paradox of the event. The flood defense system had functioned exactly as designed, executing its security protocols flawlessly and protecting itself against a perceived compromise with absolute fidelity, and in doing so had created the very disaster it existed to prevent, a catastrophic failure mode that emerged not from any component breaking, but from every component working perfectly in service of a design philosophy that had prioritized security over resilience and had created a system so thoroughly protected against unauthorized access that when authorization itself failed, no human intervention could prevent the mathematical inevitability of a city filling with its own rain, trapped inside walls built to keep the ocean out.